Okay, the 1:30 hour has arrived. Let's get this show started. Kappa 6 is still up and available. It will be due this Thursday. I think you have everything you need to do it. In fact, we're covering material we started at the very end of Friday, covering material from Kappa 7, which will not post till this Friday. There's a new reflective writing assignment up. If you haven't done last week's, please don't forget to do that, or any other ones that you might have missed. Okay, where were we? Right, so we had left on Friday talking about fluids in motion, starting the process of getting these fluids moving. And we introduced one concept called streamlines. I had a beautiful slide all prepared, and then I didn't show it. I tried to draw something similar to those streamlines in the lower right there, showing how they don't cross and how the velocity of a test particle, a test fluid element, is tangent to those streamlines. The streamlines do follow one of those fluid particles, fluid elements, as it travels through whatever contraption you have set up for that fluid to travel to. So that's a stylized one. Obviously, the upper left is a real one. This is some sort of fluid dynamics experiment where they have probably done some two-dimensional cylindrical object and had some kind of fluid, either liquid or gaseous fluid, flowing by it. And you can see how these fluid streamlines are affected by the presence of an object as they move by, in places bunching up together and in places spreading out. So our goal, one of our goals for today, is figure out what physically is happening when streamlines bunch together. What physically is happening in the fluid? When streamlines spread apart, what physically is happening to the fluid? Okay. I seem to have completely lost the top hat thing over here to the upper right. I don't seem to have any access to it anymore. I have put the attendance thing on the board, so if you have not done the attendance thing, please do that. Uh-oh. I told you I was out of it. I didn't even bring my lecture notes. It's sitting on my desk up there. The question is, do I try to wing it or do I run back and grab them real fast? I should not try to wing it. I'll be right back. Give me 2 minutes. Start the clock. What was my time? Woo! Yes. New world record. in the Newton 204 office dash. Right? This guy works out. I'm no schmo up here. Told you I was out of it today. Those of you who missed that conversation, I had to turn back twice because I had once forgotten to, and actually had my lunchbox with me. The second time I went back and replaced, well, set down the water bottle and kept the lunchbox. 3 times the charm. I don't think there's anything else I could have missed, but we'll see as we go along. Okay. We were also, actually, thanks to my next notes, I now remember what we were talking about. We had sort of written, I had tried to draw something that looked like this on the whiteboard when last we met. And we were considering water moving through a pipe and having that water move from a large diameter to a smaller diameter and thinking about what that might look like. We hadn't really gotten very far in that at all, but here we're going to introduce a concept called volume flow rate. And volume flow rate basically is going to be how much stuff is moving through this pipe. And by how much, I mean how much volume. So this is going to have units of cubic meters per second, or cubic length time per time unit. So cubic meters per second. And it's going to be through any given, you can draw any surface you like in this pipe. So here, for instance, maybe the right-hand side, we've drawn a little, you can think of it as a Gaussian surface if you want to, although it's more like it's a 1D thing and not a 3-dimensional thing, right? We're just defining this area of the pipe, and we're seeing in 1 second how much liquid, how much fluid actually passes through that point. And this is the volumetric fluid rate, flow rate. Okay, here is my, so this is just how much fluid in cubic meters, say, passes through a section of, I'll just say an area to make it more broad. I'll say a section of pipe, but it's more general than that. Through an area, through a surface. Let's say a surface. That's a better way to say it, a surface. Per unit time. Say 1/2 So this is going to have units of meters cubed per second, say, or any other length unit cubed per time unit. And basically, you can think of this, we'll call this R, the volume flow rate, basically delta V over delta T. How much volume is passing through that in a certain amount of time. Okay, here is my assertion to you. Because our fluid is incompressible, if you have a closed system, in other words, a series of pipes, or anything else where the flow is constricted to, then this has to be constant for every point along that pipe section. Okay, R must be constant for any closed system at all points in the system. Why must that be true? What would happen in this pipe if it were not the case that, say, the flow rate in this part of the pipe were different than flow rate in this part of the pipe? What would happen if that were not satisfied? Yeah, you'd have to be building up. If the flow rate isn't the same everywhere, what has to happen? You have to be gathering it in certain places and losing it from other places, right? And if you have a closed pipe and you have an incompressible fluid, that just isn't possible to do. It must be the same in everywhere in that pipe. Okay. So let's think about a formula for R that involves, let's say, the cross-sectional area and the velocity. Probably not hard to figure out what this is going to be. I'm not going to bother to force it out of you. Hopefully you can see, and in fact, this diagram is sort of leading you there, that the volume flow rate must be the surface area of whatever area it's going through times the velocity of the fluid through it. Increasing either of those, if you have the same velocity but a bigger area, that's going to increase the volume flow rate. If you have to leave the area the same but increase the velocity of the fluid through it, that's also going to increase the volume flow rate. More material will be passing through per second. So simply, area, this is the cross-sectional area of the pipe, times the velocity of the fluid. This is not volume. These are two, I've written down two V's. They are different V's. This one up here was volume. This one down here is velocity of the fluid at that point. So we've got two sections of pipe. We can write down this equation separately for each one of them. R1 equals A1 times V1. In the second section of the pipe, it must be true that R2 equals A2 times V2. But the R's have to be the same. So we can use that to say something, and since we know how the areas differ, we can use that to say something interesting about the velocities in those two sections of the pipe. So A1 V1 equals A2 V2. What does that tell us about the velocities? V1 over V2 is equal to A2 over A1. Since, for our example that we just drew, A1 is greater than A2, what does that imply about velocity 1 compared to velocity 2? Velocity 1 must be less than velocity 2. So if you have a situation like this, where you have water flowing through a large pipe and then narrow it down to a smaller pipe, it must be true that the velocity in those two sections of pipe are different. And it must be true that the velocity in pipe 2, in section 2 in this case, is higher than the velocity in section 1, because the flow rate must be the same. And you can see how they've tried to, it must be the case that the volume contained within this cylinder is the same as the volume contained within this cylinder. And so since the diameter of this cylinder is smaller, it must be that the length of the cylinder, which is generalized by a generalized way of thinking about the velocity, must be larger. This, if you think about this, say, as how much water has flown through in a second, right? Then you can see how that length will be, in fact, proportional to the velocity. And it must be that those two volumes are the same if the flow rate's going to be the same. And therefore, it must be moving a lot faster here. If you've ever canoed down a river or kayaked down a river or swam down a river, you see this play out every time the river changes in diameter, changes in depth. Whatever that volume cross-section is, again, the volume flow rate of the river, barring tributaries coming in or leaving, must be the same at all places, or what would happen, water would be pooling up somewhere. And it would be not pooling up elsewhere, be losing it elsewhere. And that's not a sustainable thing. If you're pooling up somewhere, you can only pull it up for so long before something gives, and it's a self-regulating system. Eventually that river will make it so that the flow rate everywhere is the same. And so when the river narrows down, it moves faster. That's where you get the rapids. When the river widens out, that's when it moves nice and slow. The volume flow rate must be the same in all those places. This is basically mass conservation. We can't lose or gain mass. And since our fluid is incompressible, we therefore cannot gain or lose volume. And therefore, mass conservation tells us that we must have the same amount flowing through every single part of our pipe. What will the streamlines look like for water flowing through this pipe? Let's see if we can draw them. Probably not well, but let's see if we can draw them anyway. So here's our pipe, moves from high to low. That's not horrible. I've drawn worse pipes in my day. Let's think about how the streamline is going to go. If you have a streamline at the top, what's it going to look like? It's going to be fine, going to be fine, going to be fine. Ooh, and then it's going to have to compress down and be down here somewhere. Streamline at the bottom, fine, fine, fine. And it's going to have to move up and be something like that. What about a streamline down the middle? What's it going to do? Basically, doesn't change at all. I could draw a couple more of these if I wanted to. Sure, why not? Not a great representation. You can probably find better ones online. But you get the idea. The basic idea is that these streamlines were spread far apart, and when you move them down into a more tightly confined space, again, they can't cross. They just have to get squeezed closer together. So this tells us something about the fluid for more compressed streamlines. What does that tell us about the fluid? What's happening in the fluid when the streamlines become compressed? It does mean it has a higher velocity. Kind of like when you take E fields and compress them down, you have a higher electric field strength. When you take streamlines and compress them down, you have a higher velocity of fluid through that particular area. They're analogous to electric field lines in a lot of interesting ways. So we can go back and look at the streamline picture here and see how the fluid is actually changing in velocity as it interacts with this object in its way, right? Coming along, all the streamlines are equally spaced. They have the same velocity. These streamlines here, as they interact almost directly with this object, slow down, and that's not surprising, before they manage to find a way around it. These streamlines here, again, this particular fluid element, these all get bunched together. These are moving faster through here and through here than they were out here. And that kind of makes sense because the streamline that was here has to get to here and travel a farther distance, basically in the same amount of time to get there. So it has to be moving faster as it moves over that particular part of the obstacle. You can see this is a velocity map. The closer those streamlines are together, the faster those particles are moving in that particular part of the fluid. Okay, you have some experience with this, meaning you have lots of experience. Another experience that you have with constricting the volume flow, constricting the area of something leading to a faster stream is with your garden hose. You ever been outside with a garden hose and it's, you don't have any nozzle or anything on it and it's just doing you're getting a lot of water out, but it's not going very far. If you want to spray the flowers that are really, really far away, what do? You put your thumb over the hose, over the end of the hose. What does that do? It reduces the area that the water can flow through, and therefore it will flow through faster, and therefore it will shoot further. Same sort of exact principle involved with what we just talked about. Okay, quick other thing. What if the tubes diverge or merge together? Again, this is no longer a closed system, but we can still say something. So let's say we've got, I don't know, I'm going to draw something crazy here. Some two pipes coming together, and then maybe a pipe coming off here, a pipe going over here, and a pipe coming over here or something. I don't know. Maybe water is coming in from the left and going out for the right. Maybe it could be anything. It could be coming in from this direction. Here we go. It could be coming in from this direction, out from this direction, in from this direction, and out from this direction, and from this direction. Doesn't really matter. We can say something about the flow rates through all of these pipes. And basically, in general, the sum of the flow rates in is got to be equal to the sum of the flow rates out. I'll call these J's, sure. Let's have a different, oh, not A times A times V. If you have a closed system, again, it must be the case that whatever comes in has to go out in some particular way. So this will be helpful for some of the homework problems next week. All right, let's do an example. You got a fire truck pumping water through a hose. And let's give it some numbers. Let's say the diameter of the hose is 8 centimeters and the velocity, I'll say dH, and the velocity in the hose is 0.6 meters per second, because why not? Okay, now this hose, you can draw a hose. If you've ever, firefighters use the thumb on the hose trick, except they do it with fancy equipment called nozzles instead of with their thumbs, because their thumb probably couldn't handle the volume flow rate and it would be bad news. Anyway, this looks something like this. You've got some sort of nozzle, and that nozzle restricts the flow down to a much smaller diameter. And let's say this is the nozzle. Let's say the nozzle, we don't know what the diameter of the nozzle, let's say is 1 centimeter. So it moves from 8 centimeters diameter down to 1 centimeter diameter. What is the volume flow rate going to be? No, sorry, we know what the volume flow rate is. What's the velocity going to be out of the end of the hose? We know that A of the hose times V of the hose equals A of the nozzle times V of the nozzle. We know that these A's are pi r squared. This is pi times D of the hose over 2 quantity squared times V hose times pi times D of the nozzle over 2 squared times V of the nozzle. Now some things cancel out. We don't care about this pi anymore. We can divide through by it. We can multiply through by 4, and these over 2's all go away. We really get dH squared times VH equals dN squared times Vn. We can solve this for Vn. And it is VH times the diameter, the ratio of the diameters, dH squared over dN squared. Or you could just do the division first and then square it afterwards. So this becomes, we're going to plug in some numbers, 0.6 meters per second. We've got 8 centimeters divided by 1 centimeter, quantity squared. Centimeters cancel out. 8 squared is 64. 0.6 meters per second times 64. Moving, this is a big thing. Moving the water from a 8 centimeter diameter hose down to a 1 centimeter diameter nozzle gives you a velocity increase of 1 over d squared. That's going to be a factor of 64 in the velocity. This is a large effect. 8.4 meters per second. And that stream is going to shoot a lot further than the one that was just coming out of the original hose. Okay, that's how this works. You can also talk about, and there will be homework questions about, mass flow rate. It's the same concept, except instead of talking about how much volume is flowing through, you're talking about how much mass is flowing through. These are exactly the same concept. The mass flow rate is equal to the volume flow rate. Oops. Times the density. And since the density isn't changing, you can substitute one for the other, and they're pretty much the same. This, of course, is just rho times A times V, where V is velocity. This V is for volume. This V is for velocity. It gets confusing, I'm sorry. But this is how we define the volume flow rate with velocity. Multiply that by rho, and you've got a mass flow rate. Same concept, same principles apply, same everything applies. It's just whether you want to think about mass or volume. Okay, great. The mass conservation, so flow rate and mass conservation, that the flow rates have to be the same, is one of the 2 important equations for moving fluids. The other important equation for moving fluids is the one I'm about to write down. It's called Bernoulli's equation. I know, right? It's got some gravitas to it. There's a, if you want to see a proof of how this, or derivation of this, you're welcome to look at the textbook. I think it's instructive just to write it down and try to figure out what it means, because it has some intuitive physical meaning that we might be able to glean out of just writing the equation down. So let's go ahead and do it. Here we are. P plus 1/2 rho V squared plus rho GY equals constant. That is Bernoulli's equation. We sometimes will call this constant Bernoulli's number. So, does anything strike you as familiar about this particular equation? Obviously, we've got pressure here. By the way, if you don't yet do it so that you draw your P's and rho's differently, please learn how to draw your P's and rho's differently now, because you will get very confused very quickly, because we're going to be using equations that have both of them, and you don't want to mix them up. This is, of course, the pressure in the fluid, 1/2 rho v squared. What does that look like? It looks a heck of a lot like kinetic energy, doesn't it? In fact, it's sort of some kinetic energy per unit volume, right? It's got exactly the same, 1/2 mv squared would be kinetic energy exactly for a point particle. For a continuous particle or a continuous stream of particles, 1/2 rho v squared seems like a pretty good kinetic energy term, doesn't it? That's what this is. This is a kinetic energy term. Why did I write an H? Ooh. How about this one, rho gy? What does that look like? A potential energy term. Exactly right. mgy would be some sort of potential energy term of a point mass. Rho gy will be some potential energy term in some fluid particles. Potential energy term. What is Bernoulli's equation? It is basically an energy conservation equation. We can change the energy around, change it from kinetic energy to potential energy, from potential energy to kinetic energy. As we move, again, this is going to be applicable to the same kinds of fluids we've been talking about before in an enclosed space, right? An enclosed region. Interestingly, though, pressure serves as a kind of energy, and you can change pressure into kinetic energy or pressure into potential energy and back again. You can change potential energy into pressure. You can change kinetic energy into pressure. And so pressure for fluids is the term that's added to our normal conservation of energy equation to give us Bernoulli's equation. This is a slightly more complex version of the normal kinetic energy, normal energy conservation law that we might write down in Analyte 1. Except we divided everything by volume to give a rho instead of m, and we've added that pressure term. Okay, so let's think about our pipe again. Let's keep it simple. Okay, so there's one more thing I forgot to say. Equals constant. Where is it constant? It's constant along a streamline. So each streamline within the fluid could have a different Bernoulli's number, but that fluid, for a fluid element following that streamline, their Bernoulli's number will not change as it moves through the pipe and moves faster and slower and increases pressure and decreases pressure and moves up and down. So here's an example. Again, there are more complicated streamlines here than others. Let's take the most simple streamline though, right? Which is the one that goes right down the middle. Because for that one, the relative height relative to gravity doesn't change. The y's are the same as that streamline goes across. Let's think about that streamline in this particular pipe. If y doesn't change, then, so you've got section 1 of the pipe and section 2 of the pipe. Let's just write down Bernoulli's equation on both sides. P1 plus 1/2 rho V1 plus rho GY1 must equal P2 plus 1/2 rho V2 plus rho G Y2. These are the kinds of equations you'll be writing down a lot for next week's homework assignment, right? Bernoulli's number for that streamline in section of pipe 1 must equal Bernoulli's the same Bernoulli's number in section 2 of that pipe. If y's are the same, then we can subtract both of these guys, and that term goes away on both sides. And then we have P1 plus 1/2 rho V1 must equal P2 plus 1/2 rho V2. We know how the velocities are related, though. We know that rho is a constant. We know that in this particular case, V2 must be greater than V1. What does that imply about P2? Compared to P1? It's got to be less. If V2, if this term is higher on this side than this one, then this term must be lower than this one, if those two are going to balance each other out. P2 must be less than P1. I'm getting flaky internet. That's the last thing I need. I'm just going to plug this in so that nothing else horrible goes wrong today. Okay. This implies that absent elevation changes, higher V, higher velocity, equals lower pressure. Concentrated field lines, streamlines, implies lower pressure, which is probably not intuitive. It's probably backwards of the way you would have guessed if we hadn't written the equations down and done this out from scratch. Going back to this particular picture, where is the pressure highest and where is the pressure lowest? The pressure is highest right there and right there, where the streamlines are the furthest apart and the velocity is moving the slowest. It's fastest right here, where the streamlines are bunched together. It's lowest where the streamlines are bunched together. Interestingly, you would think, you might naively think, that pushing those streamlines and those particles closer together is going to increase the pressure. It's exactly the opposite. The faster they're moving, the more, the lower the pressure actually is. This is, at some level, how airplanes work. What does the shape of an airplane wing look like? It's kind of flat on the bottom, and it's got usually a shape that looks kind of like that. So how does this work? Well, the streamlines, I'll draw this in green, on the bottom kind of go through untouched. The streamlines over the top, though, have to do something like this. And what happens? All these streamlines get compressed on the top of the wing, and they don't get compressed on the bottom of the wing. And so you have a situation where the pressure on the top of the wing goes down because that fluid is moving faster over the top of the wing. And where the velocities are moving faster, where the streamlines come together, the pressure goes down. And so this wing shape will make it so that there's a higher pressure on the wing on the bottom than there is on the top, and it will provide lift to the airplane. This actually isn't really how airplanes work. Usually it's a wing tilt that gives you more of the upward pressure than the actual shape of the wing does. But this is not an insignificant contribution to the lift on an airplane wing. So next time you're in an airplane near the window, just look out and look at what the shape of the wing is and imagine the field lines going over it and imagine where the pressures are and where the forces are pushing up on the wing, keep you in the air. Higher velocity above wing, lower pressure above wing, lift. Cool. All right, I got 10 minutes left. Let's do another example. It's about to get real. You ready? We've drawn this picture several times before. We've got some basin, we've got some water fluid filling it. Except this time, I'm going to put a little hole in the bottom of our, and so water will be freely flowing out of the bottom of this particular yeah, we'll come back to that Friday. I almost changed my mind about what I wanted to do, but I didn't. So we need to think about this is still a confined station at some point, as long as we confine ourselves to the fluid itself and not wherever it lands or whatever. We can actually think of this as a water clock. The question is, can we build a decent clock out of this? In other words, by measuring the flow rate through the bottom, maybe figure out some way to measure time in some steady way. So we need to think about the Bernoulli's equation at two of these points. And the 2 points are going to be this one and this one. So this is not the case like we had before. We're going to have to use our full Bernoulli's equation. We're not going to be able to cancel some terms out. We've got different y's, we've got different v's, we've got different pressures. Potentially, we need to think about how this is going to work. So let's say that there is, let's say this is the y at the top and this is y at the bottom. Let's say it's got some cross-sectional area at the top and some cross-sectional area at the bottom. We can write down Bernoulli's equation. We know that Bernoulli number at top, I'll call it B number at top, must equal the Bernoulli number at the bottom. It's supposed to be top and bottom. Okay. Okay, let's write it out. We know that pressure at the top plus 1/2 rho VT squared plus rho GYT, where T is all for top, must equal pressure at the bottom plus 1/2 rho VB squared plus rho GYB. Okay, let's think about pressure now. What is the pressure at the top of this tank? It's just atmospheric. There's nothing else on top of this other than the atmosphere. So we know that PT is P atmospheric. That shouldn't be too surprising to you. Okay, this is the tricky part about this problem. What is PB? And by PB, I mean right at the surface of this opening where the water is streaming out. Right. So you would think that it would be rho atmosphere. You would use your statics equation to figure out what the pressure is right here, right? You would say, well, we know it's rho naught plus whatever rho gh is delta y to get to the bottom. And you would be right if you were talking about the pressure at this point here. You are not right there. How do you know you're not right there? Sorry? You no longer have, this stuff is flowing freely out the bottom. There's no longer anything pushing up on it from below, right? Here you have stuff pushing on it in all directions, and the fluid is not in motion, which is what made that equation that we wrote down valid. Now we have fluid in motion. Remember, I warned you that some of our equations would not be valid anymore? This is a situation where one of the equations that we wrote down is no longer valid, because it's not a static, that was assuming a static situation. This is no longer a static situation. In fact, it's flowing freely through the bottom. What is the force up that the water that is actually flowing through this point at that moment feeling? Air resistance. Yeah, let's ignore air resistance. That's a good, you're right. There will be some air resistance, but let's ignore that for now. Isaac? Even if there's a big difference in height, it will just be P atmosphere. You're right. Yeah. Oh, I see. Right. Right. Assuming that the atmospheric pressure is not different in those two places. I see what you mean. That's right. It can't be so big that you have a different atmospheric pressure. Right. Assuming that that's the case, that's exactly right. You are going to have the atmosphere trying to keep this thing in, but that's it. So for this particular case, where we've got open to the air really on the top and also open to the air on the bottom, the pressure at those points are actually the same, and it is atmospheric. Now, move into the fluid a little bit over, and the pressure is going to be different. But at the actual opening where the stuff is actually flowing out, the pressure there is back to atmospheric, which is why it's getting a huge boost, which is why it's going to come squirting out fairly fast through this hole, right? So that's the most confusing part of this problem, is realizing that the upward pressure, or the pressure at all that is felt at the opening where that is coming out, is also atmospheric pressure. If you can wrap your brain around that and apply it every time you have fluid freely flowing out of a pipe in any situation, you're going to get these problems right. But that's the major conceptual hurdle to get over with these particular problems.
Dr. Steinhauer,
Yeah.
is there also, when I first thought of this, I understood that there was atmospheric pressure coming from the bottom, pushing up. But is there also pressure from the weight of the fluid above that point?
Question. So the question was, he understands, so the question from a Zoomer was, yes, there's pressure coming up from below, but isn't there also pressure pushing down from above? And the answer is yes, there certainly is pressure pushing down from above. And if that water were captured there and not able to move, the pressure would be much higher. But the fact that it is in free fall, and in fact being pushed out by the weight of the pressure on top of it, says that in fact the pressure is only due because it's in free fall. It's no longer really being influenced by anything on top of it. As soon as it comes out the hole, at the instant it's out that hole in the bottom, the pressure on top no longer has any influence on it whatsoever. So we're not talking about the instant before it comes out of the hole. We're talking about the instant after it comes out of the hole at some level. Did that answer the question?
Yeah, absolutely.
Okay, great. So now that we know that, we can start to make some headway on this problem. Basically, these are both P atmosphere and they go away. We will, I'm out of time though, finish solving this particular equation and write down the solution of what the, basically what the velocity is on Wednesday. Have a good week.